Next, we're going to talk about relative extrema. So basically maxes and mins. Okay, so we've seen that many functions have peaks and valleys. So we have a peak here, we have a valley here, we have a peak, so on and so forth. Okay, so many functions have these peaks and valleys. And knowing where these are can be very useful. And I want to demonstrate this by starting off with an example that is kind of relative to what we're going through right now, except very different function. Okay, so let's say that there's a flu pandemic. So let's say epidemiologists, they discovered a flu and it's taken over Toronto. Okay, and based on the preliminary data, the number of people in thousands who have the flu can be described by this equation. Okay, between t is equal to 0, or sorry, in between 0 and 30, where t is the number of days since the epidemic was first discovered. So what is this really quick, just looking? So I have a t squared, t, so this is a type of quadratic equation, a type of a parabola that's opening downward because we have that negative there. Now, assuming this trend continues for the flu, on what day is the epidemic expected to peak? We've heard this a lot with COVID on the news. It's like, oh, if we put these restrictions into place, can we, flatten the curve, bring it down? And if that's the case, how many days before we hit that peak so we can try to distribute resources to hospitals to help people? So things like this, especially for epidemics and pandemics, is very important to make sure you distribute resources properly so you minimize the number of deaths. Okay, so how many people are expected to have the flu on that peak day? So just thinking about a quadratic function, something that looks like this, when is the peak going to be? When's the biggest number, the maximum? It's going to be right here, okay, where the tangent is equal to 0. So when it's at that critical point. Fitting name in this case. So we'll peak when the number of people have the flu is at its max. So to find this time, we need to check when we have a horizontal tangent. All right, so let's take our derivative and see what we get. Okay, so we're going to have the negative 3 over 20. Bring down the 2, and then I have t, and then I have plus 6, and then the other term goes away because it's constant. Okay, so I have 6 over 20. We can factor out a 2, or 2 cancels rather. So I have negative 3 over 10 t plus 6. And I want the horizontal tangent, so I'm going to set this to be equal to 0. And then I need to isolate for my t. So I'll bring this 6 to the other side. Negative 6 equals negative 3 over 10 t. So my negatives go away. And I'll cross multiply. I'll bring this 10 over here. So I have 60 is equal to 3t. So our t is going to be equal to 20. Now, what does that mean? It means that since we have a downward facing parabola, the peak of the epidemic will be on day 20. How many people will have the peak at that time? Well, we have to put 20 into the equation, and then whatever that y value is, that will tell us. Okay, so I have to go negative 3 over 20, put in 20, so I have a t squared, so 20 squared, plus 6t, the t's 20, and then I had plus 20. So when you work that out, you get 80. Now remember what these numbers are. These numbers are in the thousands. So 80,000 people will have the flu on that peak day. And you can think about it that, if we have this parabola from here to here, the first 20 days, the number of people getting the flu is increasing. And then day 20 to 30, finally it's decreasing. Okay, so the max level of the epidemic, this is known as a relative or local maximum. And we will give a precise definition of this, but hopefully this motivates why this type of problem is useful for life sciences. So now let's formally define these relative maximum or local maximum, relative or local minimum. Relative and local are used interchangeably. Before we used to use local much more, but now in the recent years, people are using relative more often. So say we have a real number and it's in the domain of our function. If we look at f at that number, that's going to be a relative, okay, or local, again, used interchangeably, local maximum for f if there exists an open interval AB where C is in that interval such that f of x is less than or equal to f of C for all x in that interval. Okay, so basically if it's at the top of a peak. Okay, similarly, f of C is a relative, okay, or local, min, or minimum, for f if there exists an open interval that includes C such that it's at the bottom of a valley. So in math notation, that means f of x is greater or equal to f of C for all x in that interval. And we say that f has a relative or local extremum if it either has a relative max or a relative min. So if I want to refer to just maxes and mins in general, relative maximum in general, we call them relative extremum, or extrema for plural. So f has a relative or local extremum, or plural extrema, if there's multiple, at C, if it either has relative max or relative min. If C is an endpoint of the domain, we only consider x in the half-open interval that is in the domain. So this is debatable. It really depends on what the applications are. Some people include endpoints, the A's and B's. Some people do not. Okay, I'll make it obvious if you need to include them. And this is just to, again, give you a little bit of intuition on maxes and mins. So here we go. Where do we have tops of peaks? Well, I have one here. I also have one here, but I have to be careful. This one is a cusp. So f is not differentiable here. F is, however, differentiable here. This is where we have f prime of x is equal to 0. This is a horizontal tangent, which would correspond to a critical point. Whoops. Straight line, Janelle. Straight line. There we go. And where do I have minimum or minima? Well, I have the bottom of a valley here. And my endpoint, okay, I know it's an endpoint because there's a point here. I don't have an arrow compared to like I do on this side. This is also lower than most other places. Okay, so we'll include that for now. Now, again, this min, this corresponds to a critical number. We would have f prime of x is equal to 0 here. And the endpoints and the endpoints and the relative max here, we don't have horizontal tangent lines. Okay, so let's say I call this x1, x2, x3, x4. Okay, so this is a relative max here. This is a relative max. But these other ones, this is a relative min. And this is a relative min. Okay, so we have relative maxima at x1 and x3. And relative minima at x2 and x4. Okay, so you can pick out those things by inspection. Now, notice that the y-coordinate of these critical points correspond to relative extrema. But this does not mean that the function has a relative extrema at all critical numbers. So just because we find a critical point doesn't mean that it's going to be a maximum or a minimum. Okay, and if you think about the example as x cubed, which looks something like this, if you differentiate that and set it equal to 0, it'll tell us that x equals 0 is a critical number. But if you look at this graph, that's not at a peak or a valley. So this would not correspond to a relative extrema. So we have to be very careful. So when we find critical numbers for a function, how are we supposed to tell from the equation of the function whether those critical numbers produce these relative extrema or not? And of course, we have a test for this. We use something called the first derivative test to check this. Okay, so critical numbers are good. They don't necessarily produce extrema, a max or min, relative max or min. So we're going to use this test to allow us to check whether we will get a max or a min. Now, what does the first derivative test say? So let's say we have a critical number of a function. The function is continuous and differentiable on AB, okay, except possibly at C itself. Then we have a few different situations. The first situation is we have a relative or local maximum if our f prime of x is greater than 0 in between A and C and less than 0 in between C and B. So look at this picture right here, because that's kind of illustrating what I'm saying. So say we have functions increasing from A to C and then decreasing from C to B. Okay, so we basically have plus here and we have a negative here. Okay, this would correspond to a relative max. And when we say continuous and differentiable except possibly at C, that's the situation where we would have a corner. Okay, so this is another example where we have plus here, negative here. All right, now let's look at f of C is a relative minimum. So this is when, if we're first decreasing, okay, from A to C, and then our derivative is increasing. So something that looks like this, for example, okay, right here. So I'm going down, plus, and then I'm going up. And if you have, you're not differentiable here at the point C, but everywhere else is okay. Oops, sorry. Down, up, down, up. Then this is going to be our relative minimum. So relative max, relative min. Now, what does something look like if it doesn't have an extrema? So something similar to a cubic function. Okay, so on the left here, if I try to draw my tangents, it's going to be positive here, and it'll also be positive here, so no extrema. Similarly, if we're going the other way, say we're going downwards like this and like this, again, we don't switch if it's increasing or decreasing our function, so this is another case where you wouldn't have any extreme. Okay. So that is our first derivative test. So now let's do an example where we find all relative extrema of the functions where the function is increasing or decreasing. Okay, so same approach like we were taking before. First thing that we need is the derivative, and we need to see when it's equal to 0. Okay, so we're going to differentiate this. I'm going to get a 6x squared minus 6x minus 72. Okay, 15 goes away because it's constant. Since this is a polynomial, it's differentiable everywhere, so I don't have to worry about places where the function or its derivative does not exist. And now we're going to set this equal to 0, and we're going to find our critical numbers by solving for x. And what I'm going to do is I'm actually going to factor out a 6, x squared minus x, and then this will be minus 12, because then it'll be much easier to factor. Okay, what gives me 12? 4, 3, 6, 2, 12, 1. But I need a minus 1 here. So what I can do is I need 4 and 3, where the bigger number will be negative, so the middle term is negative. So this gives me that x plus 3 is equal to 0, or x minus 4 is equal to 0, which gives me x is equal to negative 3 and x is equal to 4. These are my critical numbers. Okay, and again, This is going to tell us how to split up our interval to check where our function is increasing and decreasing. Okay, so I have 4 here, and I have -3 here. So I'm going to split it up like this and like this, and then I'm going to make a chart to see where my function is, the derivative of my function, is positive and negative. And remember, we need to have that 6 there, okay, because we can't look at the derivative if you've canceled out that 6. And again, I'm going to pick, the numbers I seem to always default to. I'm going to do -10. Okay, so -10, -10, 0 when you're able, and let's do 10 here. All right, so -10 plus 3, this is going to be a negative. This is going to be a negative. Negative times 6 is positive. This is going to be positive. This is going to be negative. Negative times positive times 6, that's going to be negative. This is plus. This is plus. Positive times 6, that is positive. So the first interval, -infinity to -3, our function's increasing. And then it's decreasing. And then it's increasing again. So our function is increasing between -3, -infinity to -3. And then again at 4 to infinity. And then it's decreasing between -3 and 4. Now, to use the first derivative test or relative extrema, to figure out the relative extrema, I personally just like doing these little pictures. It's easier for me to visualize. So we're going upwards. Okay, so I have plus here, and then we're going down this whole time. And then afterwards, I'm going up again. Okay, so I'm doing something like this, and then I'm doing something like this. So at -3, this is going to be a relative max. And then at 4, this will be a relative min. Now, what is the actual relative max and relative min? To find the value of that, you would have to put in these x coordinates, these x points, into the actual function. Okay, so if we put in -3, we would get 150. And if I put in 4, I would get -193. This is my max, and this is my min. And if that's a little confusing, this is what our graph looks like. So to find out what that relative max and min are, I would have to put in -3 in order to get that corresponding y point. So my relative max is here. Okay, so this is my relative max. My relative min is at the bottom of the valley. Okay, so that is 4, -193. This is my relative min. And then when is my function increasing and decreasing? Well, the derivative's positive here. The derivative's positive here. And then the derivative is negative right here. Okay, so our f prime of x is greater than 0 there. F prime of x is greater than 0 there. F prime of x is less than 0 along that orange part. Okay. Let's do another one. All right, and this one, again, we're going to have to be a tiny bit careful. So first thing we're going to need is the derivative. So let's just find the derivative. So 6, bring down the 2/3, x 2/3, power 2/3 minus 1. So that's going to be a -1/3. And then I just have -4. Okay, so I end up getting, when I simplify, 6/3, that simplifies to 2. So 2 times 2 is 4 over x to the 1/3 minus 4. Okay, and I don't have any issues where f does not exist because this is all in the numerator, so that's okay. But now let's see when this is equal to 0. So I have 4 divided by x to the 1/3 minus 4. Now, what I'm going to do is I'm going to bring the negative 4 to the other side. So I get 4 is equal to 4, x to the 1/3, and then you know me, I'm not a fractions person, so I'm going to cross multiply right away. To get 4x to the 1/3 is equal to 4. My 4's can go away, okay, because they're on each side, so I can divide by 4. Now, to isolate for my x, I need to cube all of that. So I have x here, and then 1 cubed, well, that's just equal to 1. So x equals to 1, that is my critical number. But I'm still going to need to check if I have any issues where f prime of x exists. And in this case, I do have an issue because I have this thing on the denominator here. I have a part of it that's rational. So I can have that being equal to 0. So x to the 1/3 can't be 0. So if I cube everything, it means x can't be equal to 0. So what does that mean? It means that f prime at 0, this does not exist. But remember, we had no problems with f itself. F at 0 is defined. So what does that mean? It means that x is equal to 0 is a critical number. Okay, because remember, everywhere except the number itself for the derivative part. So what are our critical numbers? I have 0 and 1. Again, this tells us how to split up our interval. Okay, we can split it up like this. And then we're going to make a chart, check things in between negative infinity and 0, 0 and 1, and 1 to infinity. Okay, so we're going to do that. For this one, I think what I'm going to do is, here's my green. Let's do, I don't know, negative 1, so it's not too big. 0 and 1, probably a half is going to be easiest. This is negative 1. This is a half. And then between 1 and infinity, I don't know, let's do 2. Okay. So when we do that, plug it into Google or a calculator. This one is going to be negative. So this is less than 0. Okay, the next one will turn out to be positive. So this will be greater than 4. And then in the next one, this is just going to get more negative. So I have this. So I have that my function is decreasing, first part, increasing the second part, decreasing in the last part. So in other words, it's increasing on 0 to 1, and it's decreasing on negative infinity to 0, and 1 to infinity. So again, if I go back to my picture here for a second, I have that I'm going down here. Okay, so negative, and then I have that I'm going up. Whoops. Sorry. Plus. And then I have that I'm going down again. Okay, so I have something that looks like this in some way. All right, so at 0, this is going to be a relative min. This is going to be a relative max at 1. Now, by the first derivative test, what are these relative minimum and maximum? Well, I'll have to plug in 0 and 1. This will end up giving me 0 and 2 if I actually find out those values. So the first one, this is my relative min. This is my relative max. And again, to help you with your intuition, this is what the function looks like. So again, we have continuity at 0, but we don't have differentiability. Okay? And then I have this, so this is our relative min. And then our relative max is right here at our critical point. Okay, so this is at 1, 2. And then where's our function increasing and decreasing? Well, it's increasing from here to here. And then it's decreasing on the right of that critical point, and then in the very beginning. Okay, so this is where our derivative is positive. And these spots is where our derivative is negative. Okay. One more. More examples you see of this, the better. Let's do one where we have to do product rule. Okay, where our first function is x. Oops, sorry, my head is in the way. And then the second function is this exponential function. So product rule, the derivative of the first times the second, plus the derivative of the second. So for e, rewrite what you have, and then take the derivative of the stuff in the exponent. So derivative of 2 is 0, and derivative of minus x squared, that's just minus 2x. And don't forget, we still have to multiply this by the product rule with the first function. Okay, so let's simplify this a bit. So the first term I have e to the power of 2 minus x squared. And then I'm going to multiply these together. So I'm going to have a minus 2x squared, and I'm going to bring that to the front. Okay, you don't have to, but for me personally, it's just much easier to read. And then what I'm going to do to just make it even a bit easier to look at is I'm going to factor out the exponential part, and I'll be left with 1 minus 2x squared. That'll make it much easier to try to solve my critical point. Okay, we don't have any issues here with differentiability. We're going to set this equal to 0, and then we're going to solve for our critical numbers. Now note, remember that for this part here, our exponential function, it's always positive. It has an asymptote that approaches 0, but e to the power of 2 minus x squared, this is greater than 0 for all x. It can never equal to 0, so that means basically that part just goes away. We don't even consider it. So what am I left with? 0 is equal to 1 minus 2x squared. I need to isolate for my x, so I'm going to bring the 2x squared over. That's equal to 1. Divide by 2, 1/2. So my x, now careful, when you take the root, you get a plus minus, 1 over root 2. So this actually gives me two critical numbers, negative 1 over root 2 and positive 1 over root 2. And again, this is going to tell me how to split up my interval. Negative 1 over root 2, positive 1 over root 2. These are our critical numbers. And so just like before, we're going to make a chart between negative infinity, negative 1 over root 2, negative 1 over root 2 to positive 1 over root 2, and then positive 1 over root 2 to infinity. Now, for my numbers, what am I going to pick? This one, it's probably going to be easier to do ones and zeros. So I'm going to go negative 1, I'm going to go 0, and I'm going to go 1. Zoom in a tiny bit. So I have negative 1 here, negative 1, 0, 0, 1, and 1. Oh, and I forgot to scratch these out. But yes, this is less than 0. This is greater than 0, less than 0. So this is positive, this is negative, this is positive, positive, and then this is positive, this is negative. Okay, so our function is first decreasing, then increasing, then decreasing. So it's increasing between negative 1 over root 2, positive 1 over root 2, and then decreasing from negative infinity to negative 1 over root 2, and 1 over root 2 to positive infinity. And again, to draw our little picture, to better see whether we have mins or maxes, first we're going down, then we're going up, then we're going down again. Okay, so minus, plus, minus. So we have something like this. So our first one, this is going to be a relative min. Our second one is going to be a relative max. Okay, and by the first derivative test, you know, what are these things? So approximately when you plug it into your calculator, you should get negative 3.17 and then positive 3.17. So that first one there, that's the relative min. Second one, that's the relative max. And again, just to help build your intuition on what the function looks like, Okay, so we have our critical numbers here. So 1 over root 2, f of 1 over root 2 with the horizontal tangent. We have the one in the valley here, negative 1 over root 2, f of negative 1 over root 2. Okay, that's where our tangents are horizontal. And where is the function decreasing? This first part, and then the last part, and then in the middle, that's where the function is increasing. So the green parts, that's where f prime of x is less than 0. And the orange part, this is where f prime of x is greater than 0. All right. So lots of examples. Hopefully you found that helpful and straightforward to follow. Thank you very much.